Okay, so now we're going to use this information in a two-part problem. So starting from the beginning here, you are asked to administer a drug in 1 liter of fluids to a 22-pound dog. The drug is dosed as a rate of 75 milligrams per kilogram, and the supply is listed as a 1.25% concentration. After the drug has been added to the 1 liter of fluids, the total volume is to be infused over an 8-hour period with an IV set calibrated to 40 drops per milliliter. So the first question, how much of the drug should be added to the 1 liter of fluids? And the second question, what is an observable drip rate for this infusion? So to answer question A, this is a straightforward drug dosage calculation. So for part A, what we want to do, as I move it to a pen, there we go, is we are going to take our 22 pounds and do just like we did back in chapter 2. We are going to convert this into a volume of drug to administer. So 1 kilogram is 2.2 pounds. We know that we want to give 75 milligrams for every 1 kilogram of body weight. And we know that based on the drug supply of 1.25%, when we multiply that by 10, we take our 1.25 and multiply it by 10, that means that in 1 milliliter of fluid, there are 12.5 milligrams. So when you go ahead and do the computation for part A, you find out that you want to take 60 milliliters of drug and add to the 1 liter of fluids. So the total volume to be infused is going to be 1,060 milliliters. And now the second part is going to be an observable drip rate calculation. So we know how much to infuse, that's our 1,060 milliliters. We know this is going to be done over 8 hours. And we know that the IV set is calibrated to 40 drops per milliliter. So following on the previous video, we're going to take our total volume, 1,060 milliliters, which is going to be infused over an 8-hour period. And as we did before, the first thing I'm going to do is change hours into seconds, because we're going to find our unit rate of drops per second. And now multiply by the 40 drops per milliliter. So the hours cancel, the milliliters cancel, and we are left with drops over seconds. So when you do the calculations here, you do not come up with a nice, neat, easy number. You basically come up with about 1.47 drops per second. Clearly, this is not observable. So the question becomes, what would make an observable drip rate? Well, again, you have to finesse this a little bit. So if we were to take this and multiply it by 30, so if you take the 1.47 times 30, you come up with about 44 drops in 30 seconds. When you actually do the calculation, it comes up to 44.1, but of course you'd round that to about 44. So that's 44 drops in 30 seconds, which could certainly be something observable. If you want to try another another interval of time, you could take the 1.47, and multiply it by 40 to see what you get for a 40-second interval. So 1.47 times 40 gives us 58.8. So that's approximately 59 drops in 40 seconds. Also an observable quantity. So basically either of these is going to work. So we started off with something that was a unit rate, number of drops in 1 second, which clearly we're not going to observe. And again, we just had to finesse it a little bit. See what happens in 30 seconds, see what happens in 40 seconds. You could also go all the way to a minute. Just multiply the 1.47 by 60. if you do that, you get 88.2, or about 88 drops per minute. So if you want to stand there for 60 seconds and see if 88 drops go by, that's perfectly fine as well. So that's basically it. So part A, the volume to be added to the fluids, 1 liter of fluids, and part B, determining a unit drip rate, which then we can convert into an observable drip rate.